Look up at the night sky. That faint milky band, it's our home, the Milky Way seen from within. Beyond it, the universe is a vast ocean, dotted with countless islands of light, galaxies. Each galaxy is a colossal city of stars, gas, and dust, bound by gravity and home to cosmic drama. But not all galaxies fit the classic spiral or elliptical mold. Some are cosmic outliers, rebels shaped by collisions and strange processes we're only beginning to understand. These galaxies defy neat classification, challenging our ideas of how the universe works. Today, we'll journey across intergalactic space to explore 10 of the strangest galaxies known to science. From galactic collisions to mysterious rings, prepare to see the cosmos in a new light. Let's step aboard our ship of the imagination and begin. The universe is waiting. Our first stop is the Cartwheel Galaxy, 500 million light-years away. A brilliant blue ring surrounding a yellow core like a cosmic bullseye. Formed by a smaller galaxy plunging through a larger one, this shockwave of star formation is a beautiful scar left by a cosmic collision. Next, Hoag's object, a near-perfect ring of young blue stars encircling an older yellow core, separated by a mysterious dark gap. Its formation remains a puzzle. No clear evidence of collision, no bar instability, just a cosmic enigma. And through its ring, another distant ring galaxy photobombs, a mystery within a mystery. The Sombrero Galaxy, seen edge-on, resembles a wide-brimmed hat with a bright central bulge and a thick dust lane. It boasts an unusually rich population of ancient globular clusters and a supermassive black hole at its core. Its structure hints at a complex, possibly violent past, perhaps a merger of two very different galaxies. MEM64, the Black Eye Galaxy, features a dark dust band across its bright nucleus, a cosmic black eye. Its outer regions rotate opposite to the inner ones, evidence of a past merger that left behind turbulence and new stars. The antennae galaxies are two spirals colliding, their tidal tails stretching out like insect antennae. This chaotic merger triggers a firestorm of star formation, a glimpse into how galaxies grow through cosmic collisions. The Tadpole Galaxy, with its bright head and long tail, looks like it's swimming through space. A smaller galaxy's gravity pulled out this spectacular tail, a fleeting moment in a galaxy's dramatic life. Mael's object, or ARP-148, is a ring with a rod piercing through, a cosmic question mark born from a precise, violent collision. It's a rare snapshot of galactic transformation, frozen in time. The Sunflower Galaxy, M63, is a flocculent spiral with patchy, petal-like arms, chaotic, beautiful, and shaped by bursts of star formation. Its delicate appearance hides a history of devouring smaller galaxies. The Whirlpool Galaxy, M51, is a perfect spiral, its beauty sculpted by the gravitational pull of a smaller companion. This cosmic dance triggers waves of star formation, proving that even perfection is born from disturbance. The Andromeda Galaxy, our nearest major neighbor, is a galactic cannibal, its halo filled with remnants of galaxies it has consumed. But its strangest feature? It's heading straight for us. In 4.5 billion years, Andromeda and the Milky Way will collide, merging into a new giant galaxy, our cosmic destiny. From cosmic bullseyes to impending collisions, these galaxies reveal a universe far stranger and more dynamic than we imagine. Each is a clue to how galaxies form, interact, and evolve. By studying these outliers, we push the boundaries of our understanding and glimpse our own origins. The universe is ever-changing, filled with mysteries waiting to be discovered. For every answer, new questions emerge, fueling our curiosity and wonder. Subscribe and join us as we continue exploring the magnificent, mysterious cosmos together.
Have you ever looked up at the night sky and wondered, is any of this real, or could our entire existence be an advanced computer simulation? This isn't just science fiction. Some of the brightest minds in philosophy and science debate it seriously, challenging our most basic assumptions about reality. If we can create virtual worlds, what's to stop a far more advanced civilization from simulating an entire universe, ours? So, what exactly do we mean when we talk about a simulation? It's a concept that's become increasingly prevalent in science fiction, but it also has roots in serious philosophical and scientific inquiry. Think of a video game, a world with its own rules, its own physics, and its own set of possibilities. Everything within that game operates according to a predefined set of instructions, where characters act only as the code allows. Their actions, their interactions, everything is dictated by the underlying programming. The simulation hypothesis suggests, in a rather mind-bending way, our universe might work the same way, that what we perceive as reality could, in fact, be a highly sophisticated computer program. Its laws of physics could be programmed rules. The very fabric of space and time might be governed by lines of code. The speed of light, for example, might be a processing limit, a constraint imposed by the computational power of the system running the simulation. Not a fundamental law of nature, but rather an artificial barrier. At the quantum level, where the universe behaves in strange and unpredictable ways, reality looks pixelated. Energy comes in tiny packets, discrete units, like pixels on a screen. This granularity at the smallest scales could be evidence of an underlying digital structure. If the universe is a simulation, it would make sense for it to be built from the smallest possible units, the fundamental building blocks of reality, just as digital images are built from pixels. It's an elegant and efficient way to construct a complex system. Who would run such a simulation? What kind of being or entity would have the capability and the motivation? Maybe a future civilization far more advanced than our own, or an alien species, with technology beyond our comprehension, for reasons we can only guess, perhaps for scientific research, historical recreation, or even just for entertainment. The possibilities are endless and the truth remains elusive. Why take this idea seriously? Our own technology is a clue. Video games have evolved from simple blocks to photorealistic worlds. Philosopher Nick Bostrom's thought experiment: if advanced civilizations can run countless ancestor simulations, statistically, we're more likely to be in one of them than in the original reality. The universe's physical constants seem fine-tuned for life. Maybe they're programmed that way. The universe is profoundly mathematical, as if it's running on code. If reality is mathematical, maybe it's computational too. So if we entertain the idea that our reality is a simulation, a meticulously crafted digital world, could we possibly stumble upon some kind of tangible proof? Is there a way to peek behind the curtain? Some physicists are actively looking for what they call glitches, subtle anomalies or inconsistencies in the very laws of physics that govern our universe. These could be tiny cracks in the code, so to speak. One potential clue might lie in the Planck length, considered to be the smallest possible unit of space that exists, the fundamental building block. The theory suggests that if space-time itself is structured like a grid, then high-energy particles, when accelerated to tremendous speeds, might behave in unexpected or differently. Another intriguing idea revolves around computational shortcuts. The thought is, maybe the universe only fully renders the fine details of reality when it is being directly observed, closely echoing some of the most profound mysteries of quantum mechanics and observation. But the challenge of finding such subtle glitches is incredibly tough, because what might initially appear to be a bug in the system could, in reality, simply be a manifestation of new, undiscovered physics. Extraordinary claims, especially those challenging our fundamental understanding of reality, demand extraordinary evidence to back them up. So, for now, the matrix, or whatever underlying reality exists, remains seemingly seamless and without any obvious flaws. Not everyone is entirely convinced by the simulation argument. Some scientists and philosophers remain skeptical, raising valid points and alternative perspectives. The simulation hypothesis fundamentally assumes that future civilizations would not only be capable of running such detailed and complex simulations, but also that they would actively want to do so. But maybe they wouldn't. Perhaps they'd find it unethical or simply a waste of resources. Simulating a universe that is as complex and intricate as ours could potentially require more computational power and resources than the universe itself actually contains. The energy requirements alone would be astronomical, The fine-tuning argument, which suggests the universe is specifically designed for life, has a counter-argument, the anthropic principle. This principle states that we observe a life-friendly universe simply because we are here to observe it. If the universe weren't life-friendly, we wouldn't exist to ask the question. Ultimately, the simulation hypothesis in its current form may be fundamentally unfalsifiable, because if the creators of the simulation are sufficiently advanced, they could effectively hide all evidence of its artificial nature. And if a theory can't be rigorously tested or potentially disproven through experimentation, does it truly fall within the realm of science, or does it remain primarily a philosophical concept? It's undeniably a fascinating and thought-provoking idea, but it may very well always remain beyond the reach of definitive experimental proof, residing in the realm of theoretical possibility. So, does it matter if we're in a simulation? In daily life, probably not. The love you feel, the beauty you see, these are real to you, no matter the universe's source code. What matters is the question itself. It drives science and human curiosity. Whether reality is programmed or natural, our quest to understand it is the grandest adventure. The simulation hypothesis reminds us to keep questioning, keep exploring, and never lose our sense of wonder. Keep looking up. When you look up at the night sky, you're seeing history, light that began its journey long before you were born. Every star is a message from the past, a glimpse into a universe that once was. Telescopes are our time machines, letting us witness events from millions or even billions of years ago. The universe is so vast that even light, the fastest thing there is, takes ages to cross it. When we point a telescope at a distant object, we intercept ancient light, an echo of a star's past. The night sky becomes a dynamic map of cosmic history, each direction a corridor into a different era. The farther we look, the deeper into the past we see. Our most powerful telescopes are tools for uncovering the universe's autobiography, photon by photon. We can witness the birth of stars, the deaths of supernovae, and the dance of galaxies, all by collecting ancient light. The night sky is a museum of cosmic time, and telescopes are our keys to its secrets. Light travels at nearly 300,000 kilometers per second, fast enough to circle Earth 7 times in a second. But in the cosmos, even this speed means every image is delayed. The sun's light takes over 8 minutes to reach us. We see it as it was, not as it is. If the sun vanished, we'd bask in its light for 8 more minutes, unaware. The nearest star system, Alpha Centauri, is 4.3 light-years away. Its light left before some of us started university. Polaris, over 430 years old by the time it reaches us. The Orion Nebula's light began its journey as the Roman Empire faded. Every star you see is a ghost from the past, some recent, some ancient. The farther we look, the older the light. This is the reality of a universe where the speed of light, though immense, is not infinite. We are always looking into the past. A telescope's real power isn't magnification, it's collecting light. Think of it as a giant bucket, gathering faint photons from distant objects. The bigger the mirror, the more ancient light it can catch. Distant galaxies are incredibly faint. Their light is stretched thin by the time it reaches us. Our eyes can't see this trickle, but a large telescope can, over hours or days. That's why astronomers build ever larger telescopes to see further back in time. Telescopes like Hubble and James Webb stare at tiny patches of sky, collecting light from galaxies born when the universe was young. Each increase in mirror size pushes our vision deeper into cosmic history. By capturing this ancient light, we're collecting fossils, not of bone, but of the universe itself. The reward, glimpsing the dawn of time. With powerful telescopes, we conduct cosmic archaeology, piecing together the universe's history. The most distant galaxies we see are over 13 billion years old, from when the universe was just a few 100 million years young. This cosmic dawn marks the birth of the first stars and galaxies. These early galaxies are small and chaotic, unlike the grand spirals we see nearby. By observing galaxies at different distances, we create a photo album of cosmic evolution. The light from these objects reveals the elements present in the first stars, mostly hydrogen and helium. Heavier elements like carbon and iron were forged in these stars and scattered when they died. Looking back lets us witness the beginning of the cosmic recycling that made planets, and us, possible. Comparing what we see with our theories helps us refine our understanding of the universe. Sometimes the universe surprises us, pointing the way to deeper discoveries. Telescopes let us see into the past, connecting us to the universe's unfolding story. Every distant galaxy is an ancestor of our own Milky Way. The light we capture tells how the universe evolved from simple gases to the complex cosmos we know. The laws that guide ancient photons are the same ones shaping our world. By studying ancient starlight, we probe mysteries like dark matter and dark energy. The universe's past holds the key to its present and future. The elements in our bodies were forged in stars long ago. We are stardust. When we look at ancient stars, we glimpse our own origins. Each photon is a messenger from a world that may no longer exist, a whisper from the deep past. With our telescopes, we're learning to listen, understand, and marvel at our place in the cosmos. Have you ever looked up at the night sky and wondered what's really out there? Imagine if you could see the entire universe at once. Every star, every galaxy, every point of light. The darkness would vanish, replaced by a breathtaking tapestry stretching from horizon to horizon. Our curiosity has always driven us to explore, to ask, where did we come from? Are we alone? The universe is vast. Billions of galaxies, each a city of stars, each star a potential sun for other worlds. To see it all would be humbling, showing us how small we are, yet how connected to something magnificent. We'd witness the birth of stars, galaxies colliding, and the remnants of ancient explosions. The entire history of the cosmos would unfold before us, a story written in light. Our own origins would be there, connecting us directly to the stars. This vision would reveal the full story of our universe from its beginning to now. It's the ultimate dream, to see the complete picture of everything that exists. If we could see the whole universe, it would be like gazing across a vast cosmic ocean dotted with islands of light. Galaxies, spirals, ellipticals, irregulars, each galaxy a unique world, home to billions of stars. We'd see giant red stars, tiny neutron stars, and blazing blue giants. A dazzling variety. Between the stars, glowing nebulae would reveal cosmic nurseries where new stars are born. These clouds are the building blocks of the cosmos, the raw material for new solar systems. We'd witness the invisible galaxies held together by dark matter, the universe expanding, black holes warping space. The mysteries of dark energy and gravity would be on display, challenging our understanding. Every corner would offer new wonders and new questions. The universe would become a living laboratory, its secrets open for us to explore. We'd see the forces shaping everything, from the smallest star to the largest galaxy. The cosmic ocean would be ours to navigate to. With this cosmic view, our search for other worlds would transform. We'd see exoplanets as tiny lights orbiting distant suns, trillions of them, each a potential home. Our solar system would be just one of countless others. We could spot Earth-like planets in the habitable zone, where liquid water and maybe life could exist. Analyzing their atmospheres, we'd search for water, oxygen, or other signs of life. Even the simplest life elsewhere would be a profound discovery, answering the question, are we alone? And what if we found signs of technology, city lights, vast structures, or something unimaginable? The possibility of other intelligent beings would change our perspective forever. We'd see ourselves as part of a larger cosmic community. The universe would feel both bigger and more connected. It's a humbling, thrilling thought. Seeing the universe in its entirety would unite us as Earthlings, making our divisions seem small. We'd all share the same magnificent sky, inspiring global cooperation and a new age of discovery. Scientists would race to understand this flood of new data, sparking breakthroughs across every field. Young people would dream bigger, inspired to explore and learn. Art, music, and stories would be transformed by the beauty of the cosmos. The universe would become a central theme in our culture, fueling creativity and wonder. This dream connects us to our ancestors, who looked up and wondered, building monuments and myths. We'd be continuing their journey, fulfilling a timeless human desire to understand the cosmos. By seeing the universe, we'd honor generations past and inspire those yet to come. The quest to know the cosmos is a shared human story. It's a dream as old as humanity itself. Seeing the universe would change how we see ourselves and our world. Our daily struggles would shrink against the backdrop of billions of galaxies. We'd realize how precious and fragile Earth is, inspiring us to protect it. This cosmic perspective could motivate us to create a better future. The universe's endless possibilities would give us hope and drive us forward. It would be more than science. It would be a spiritual experience, connecting us to something greater. We are made of stardust. Seeing the stars is seeing a part of ourselves. Let's keep looking up, building telescopes and exploring. Every discovery brings us closer to that ultimate vision. The quest to understand the universe unites us, inspires us, and brings out our best. It's a dream worth striving for, a new dawn for all humanity. When we look at the night sky, we're seeing just our universe, a vast expanse containing all the stars, galaxies, and planets we can observe. For centuries, we thought this was everything, but modern physics suggests our universe might be just one of many. The multiverse is the idea that our universe is a single bubble in a much larger cosmic ocean, with countless other bubbles, other universes, each with their own laws and histories. This isn't just science fiction. Theories like string theory and cosmic inflation naturally predict the existence of other universes. The distinction is profound. Our universe is what we can see and measure, while the multiverse is the hypothetical collection of all possible universes. It's a shift as dramatic as realizing our sun is just one star among billions. The multiverse challenges our sense of uniqueness and expands our cosmic perspective. It's a humbling, mind-expanding idea, one that redefines our place in reality. The story of the universe may be just one chapter in a much grander cosmic saga. Why do scientists take the multiverse seriously? It starts with cosmological inflation, the theory that our universe expanded at breakneck speed just after the Big Bang. Inflation explains why the universe is so big and uniform, and its predictions match observations. But the math suggests inflation didn't just happen once, it could be happening endlessly, spawning new universes all the time. String theory adds another layer, proposing that the fundamental building blocks of reality are tiny, vibrating strings, and that extra dimensions shape the laws of physics in each universe. With countless ways these dimensions could be arranged, string theory predicts a vast landscape of possible universes, each with its own rules. Our universe is just one configuration among many. The multiverse isn't a wild guess. It's a natural outcome of our best theories. It suggests our universe's laws aren't unique, but just one set among countless possibilities. There are several ways scientists imagine the multiverse. The bubble universe model, from eternal inflation, envisions our universe as one bubble in a boiling cosmic sea with new universes constantly forming. The many worlds interpretation of quantum mechanics suggests every quantum event splits reality, creating parallel universes for every possible outcome. String theory's brain multiverse imagines our universe as a three-dimensional brain floating in higher dimensional space with other brains, other universes nearby. Some theories even propose that brains could collide, triggering events like our Big Bang. And if space is infinite, then somewhere out there, regions identical to ours must exist another Earth, another you living a parallel life. These models differ, but all point to a reality far bigger and stranger than we once imagined. The multiverse could be a bubbling sea, a branching tree, or an endless expanse of repeating possibilities. Each theory stretches our imagination and our science. If infinite universes exist, every possible outcome happens somewhere. Life on Earth might not be a miracle, but an inevitability, guaranteed to arise in some universes. This is the anthropic principle. We find ourselves in a universe suited for life because we couldn't exist anywhere else. It explains why our universe seems so finely tuned for life. There are countless universes, and we're in one where the conditions are right. But if every choice spawns a new universe, do our decisions matter? It's a question that's both unsettling and liberating. The multiverse challenges our ideas of chance, meaning, and uniqueness. Testing the multiverse is hard, but scientists are searching for indirect clues, like faint imprints in the cosmic microwave background. Finding such evidence would revolutionize our understanding of reality. The multiverse is the ultimate frontier, pushing us to rethink what's possible. It's the next step in a long tradition, expanding our view from Earth to the solar system, to the galaxy, to the universe, and now perhaps to the multiverse. Exploring these ideas drives physics forward, forcing us to test and refine our theories. But the multiverse remains a hypothesis, no direct evidence yet, and many scientists remain skeptical. The debate is healthy, keeping science rigorous as we explore the unknown. Whether or not we ever prove the multiverse, the search itself expands our understanding. Our place in the cosmos may be smaller than we thought, but our curiosity is boundless. The story of the multiverse is still unfolding, and its ending could change everything. Have you ever seen a hologram, maybe on a credit card? At first it looks flat, but tilt it, and suddenly a 3D image appears. This is the magic of a hologram, a flat surface encoding all the information needed to project a three-dimensional image. Unlike a photo, which captures light from one angle, a hologram records the interference patterns of light, capturing both intensity and depth. The process involves splitting a laser beam. One part shines directly on a plate, the other bounces off the object, and together they create a pattern that encodes the object's 3D shape. Shine light through the developed plate, and the original image springs to life in 3D. The key idea: all the data describing a 3D object can be stored on a 2D surface. This concept isn't just a physics trick, it's a profound principle about information. The 3D image is a projection generated from a simpler, flat reality. This idea has leapt from the lab into cosmology, raising one of the most mind-bending questions in science. Could our universe itself be a kind of hologram? Let's find out. Imagine stretching the hologram idea to the entire universe. What if our three-dimensional world is actually a projection from a distant two-dimensional surface? This is the holographic principle. Everything we see, from galaxies to atoms, could be a 3D image of information stored on a cosmic boundary. It's not that the universe isn't real, just that its true nature might be encoded elsewhere. This idea emerged from the clash between Einstein's gravity and quantum mechanics, especially in extreme places like black holes. The holographic principle offers a new way to think about space, time, and information. Imagine the universe as a sphere, with the real physics happening on its 2D surface, projecting everything inside. It's a radical shift. Are we living in a cosmic projection? The story begins at the edge of a black hole. Black holes are so dense that not even light escapes, and at their core, physics breaks down. In the 1970s, Stephen Hawking discovered black holes emit radiation and slowly evaporate. This led to a paradox. If a black hole evaporates, what happens to the information it swallowed? Physicists found that a black hole's information content depends on the area of its event horizon, not its volume. It's as if a warehouse's storage depended only on its walls, not its size. This was the first clue that information in a volume could be described by its surface, a seed for the holographic principle. Maybe the universe itself stores its information on a cosmic boundary. How can a 2D surface generate our 3D universe? The answer lies in information. The holographic principle suggests the hard drive of reality is two-dimensional. One powerful tool is the ADAS-CFT correspondence, a mathematical bridge between a universe with gravity and a boundary without it. Anything happening in the 3D universe has a matching description on the 2D boundary. This lets physicists tackle tough questions about gravity by translating them into simpler boundary-based problems. If true, space and gravity are emergent, illusions woven from quantum bits on the cosmic edge. The real, fundamental reality is the information on that boundary. Our universe could be the grandest hologram of all. The holographic principle is still a theory, not a proven fact. Some physicists champion its mathematical beauty and power to resolve paradoxes. Others remain skeptical, noting it's based on models unlike our universe. There's no direct experimental evidence yet. Scientists search for clues in the cosmic microwave background and in experiments looking for holographic noise. So far, the evidence is elusive, but the quest continues. Whether true or not, the holographic principle pushes us to question reality itself. Are we living in a cosmic hologram? We don't know yet, but the search reveals the boundless curiosity of the... Have you ever looked up at the night sky and wondered if we're truly alone? What if, just beyond our senses, another version of you is asking the same question? Modern physics suggests our universe might be just one bubble in a vast cosmic ocean of worlds. Our senses are limited, but science reveals reality is far stranger than we imagine. Imagine every choice you make splitting reality. Countless versions of you, each living a different life. The idea of parallel universes isn't idle speculation, it's a serious scientific pursuit driven by the logic of our best theories. The answer to whether we're alone may be more astonishing than we ever dreamed. So what exactly are parallel worlds? It's a concept that has captured the imagination of scientists and science fiction enthusiasts alike. Picture our universe, the one we know and experience, as a single page, filled with all its complexities and wonders. Now imagine that page existing in an infinite book, a vast collection of stories beyond comprehension. Each page in this book represents a separate universe, a distinct reality with its own unique story, its own set of physical laws, and its own unfolding narrative. These aren't just distant planets within our own universe, but entirely separate realities, realms that are fundamentally unreachable by any spaceship or technology we can currently conceive of. Some theories, often explored in theoretical physics, suggest that these parallel worlds could be nearly identical to ours, differing only in the most subtle of ways, perhaps only in something as trivial as what you happen to have for breakfast this morning. Others, however, imagine universes with completely and radically different physical laws, where the very building blocks of matter, atoms, or even the shining stars themselves might not even exist in the way we understand them. In a way, the multiverse, if it exists, could be seen as a grand experiment on a cosmic scale, nature trying out every possible set of rules and conditions to see what emerges. For the most part, these worlds are likely forever out of our reach, separated by distances and fundamental differences we can scarcely imagine. But even the mere possibility of their existence suggests that reality is far more expansive, far grander, and far stranger than we have ever dared to think. The possibilities inherent in a multiverse are truly endless, and ultimately far stranger and more awe-inspiring than anything we could ever create in fiction. The concept of a multiverse, while seemingly fantastical, actually emerges from the very foundations of real science. It's not just a philosophical musing, but a potential consequence of our current understanding of physics. Eternal inflation, a refinement of the Big Bang theory, suggests our universe's explosive birth was just one event in an ongoing process, with each inflationary event creating a new, distinct universe bubble, potentially with its own unique physical laws. Quantum mechanics, the physics of the very small, adds another mind-bending twist. The many worlds interpretation proposes that every quantum event, every decision at the subatomic level, splits reality, spawning countless parallel universes, each representing a different possible outcome. Every moment at every quantum intersection, new branches of reality are created, each as real, as valid, and as physically present as our own. String theory, another leading contender for a theory of everything, proposes the existence of extra hidden dimensions beyond the three we experience directly. Within this framework, our entire universe could be confined to a three-dimensional brain, essentially a membrane floating within a larger, higher-dimensional space. And if our universe is a brain, then other brains, other universes, could be incredibly close, perhaps just a millimeter away in that higher-dimensional space, yet forever hidden and inaccessible to us. These multiverse theories aren't just wild, speculative guesses. They're logical, and in some cases unavoidable extensions of our best and most successful attempts to explain the fundamental nature of the cosmos. If any of these theories hold true, then we're living on just one tiny twig, on an infinite branching cosmic tree of universes, each with its own unique history and destiny. Ultimately, the multiverse may represent the ultimate consequence, and perhaps the most profound mystery of our ongoing search for understanding the universe and our place within it. We can't visit parallel universes, but scientists search for clues. The cosmic microwave background, the afterglow of the Big Bang, might show scars from collisions with other universes, though none have been confirmed. The fine-tuning of nature's constants could hint at a multiverse, countless universes, each with different settings, and we just happen to be in one that supports life. Quantum computers might even tap into parallel realities to perform their calculations, according to some interpretations. The Large Hadron Collider could reveal extra dimensions, offering indirect evidence for other universes. While nothing is proven, each discovery pushes the boundaries of what we know about reality. The search continues, blending imagination with rigorous science. The quest for parallel worlds is about more than simple curiosity. It's a fundamental drive, pushing us to explore the very edges of what we know. It's about understanding reality itself, peeling back the layers of the universe to reveal its deepest secrets and underlying structure. Each scientific revolution has humbled us, challenging our preconceived notions and expanding our understanding, showing we're not the center of everything, but rather a small part of a much grander cosmic tapestry. The multiverse is the next step in this ongoing intellectual journey. Theories like string theory with its extra dimensions and vibrating strings, and inflation, the rapid expansion of the early universe, aim to solve deep puzzles about the fundamental nature of reality and the origins of the cosmos. And the multiverse is often a natural outcome, a compelling consequence of these theoretical frameworks. If proven, the multiverse would reshape our sense of purpose, forcing us to reconsider our place in the grand scheme of existence, and place in the cosmos, challenging our assumptions about uniqueness and cosmic significance. It would mean we're not just ordinary beings in an ordinary universe, but potentially one of countless variations, but part of an infinite ensemble, a small piece of an unimaginably vast and diverse cosmic landscape. The journey is just beginning, and the path ahead is filled with uncertainty and profound possibilities. But the search is essential, for it speaks to our deepest desires to understand the universe and our place within it. The ultimate expression of human curiosity, driving us to explore the unknown and push the boundaries of knowledge. So next time you look at the stars, wonder, what stories are unfolding in all the other worlds, and what secrets does the multiverse hold?
Hello and welcome, fellow stargazers. I'm King, your guide for this celestial journey. And today, we're embarking on a cosmic safari, a thrilling expedition into the heart of our galaxy. We'll be venturing through the Milky Way's strangest stars, those celestial oddities that defy expectations. The night sky may look peaceful and serene from our earthly vantage point, but beneath that tranquil facade, it hides a universe teeming with the bizarre, the extreme, and the utterly fascinating. It's a cosmic playground of wonders. We'll meet stars with magnetic fields so powerful that they could erase your credit card from the moon, or even disrupt spacecraft electronics with their intense electromagnetic forces. We'll encounter cosmic lighthouses, also known as pulsars, spinning faster than blenders, emitting beams of radiation that sweep across the cosmos. And we'll witness stellar giants shedding their mass in spectacular displays, creating breathtaking nebulae as they approach the end of their lives. These aren't just mere points of light in the vast darkness. They're dynamic engines of creation and destruction, constantly shaping the universe around them. So, buckle up and prepare for an unforgettable ride. By the end of our journey, you'll see the night sky with a newfound awe and appreciation for its weirdest, most wonderful, and truly mind-blowing inhabitants. Let's delve into the realm of the extraordinary, where cosmic forces reign supreme. First up, magnetars. These celestial objects represent some of the most enigmatic and powerful entities in the universe. They are the universe's ultimate magnets, possessing magnetic fields that dwarf anything we can comprehend on Earth. These fields warp space and time around them. Born from the fiery hearts of massive stars, their existence is a testament to the extreme conditions that can arise in the cosmos. These stellar giants meet their dramatic end in cataclysmic supernovae, events where the star's core collapses in on itself. From the ashes of these explosions, Magnetars emerge as a special type of neutron star, incredibly dense and rapidly spinning remnants of their former selves. These aren't your everyday neutron stars. Magnetars boast magnetic fields a quadrillion times stronger than Earth's, a force so immense it's hard to fathom. Get too close to one of these cosmic behemoths, and their magnetic fields would tear your very atoms apart, disrupting the fundamental building blocks of matter. These intense fields trigger starquakes on the magnetar's surface, violent shifts in its crust. These quakes unleash bursts of gamma rays so powerful they've been detected affecting Earth's atmosphere even from across the vast expanse of the galaxy. Only a few dozen magnetars are known to exist in our galaxy, making them incredibly rare celestial objects. Each one serves as a rare laboratory for exploring physics at its most extreme, pushing the boundaries of our understanding. Their exact origins remain shrouded in mystery, but their immense power is unmatched by almost anything else we know of in the universe. Magnetars push the known laws of nature to their absolute limits, challenging our understanding of the cosmos. Next, meet pulsars, rapidly spinning neutron stars discovered in 1967. They emit beams of radiation from their poles, sweeping across space like cosmic lighthouses. Some spin hundreds of times per second, more precise than any clock on Earth. Their regular pulses let us test Einstein's theories and even detect gravitational waves. The first binary pulsar system proved these ripples in space-time decades before we saw them directly. Pulsars are not just lighthouses, they're cosmic metronomes, revealing the universe's deepest secrets. Their precision is a gift to science. Now, let's meet the Wolf-Rayet stars, massive, dying giants blasting their outer layers into space. Their fierce winds strip away mass at millions of kilometers per hour, exposing hot, heavy element cores. These stars are among the hottest known, creating glowing nebulae like cosmic graffiti. Wolf-Rayet stars forge and scatter the elements that make planets and life possible. They live fast, die young, and enrich the galaxy with every breath. Their violent ends seed the cosmos for new generations of stars. In ancient star clusters, some stars break all the rules. Blue stragglers. These hot, young-looking stars shouldn't exist among their elderly neighbors. They're likely formed when one star siphons material from another, or when two stars collide and merge. This cosmic vampirism or collision resets their clocks, making them shine blue and bright. Blue stragglers remind us that even in the cosmos, there are exceptions to every rule. Star clusters are dynamic, not static, full of surprises. Our final stop on this cosmic tour brings us to a truly awe-inspiring class of stars. Behold, red supergiants. These celestial behemoths represent the extreme upper limit of stellar size. They are, quite simply, the largest stars by volume in the known universe. To truly grasp their scale, consider this. Once massive main sequence stars, they've expanded dramatically as they age, growing so large they could engulf entire planetary systems. Their outer layers become incredibly tenuous, with a density thinner than air here on Earth. These stars are truly diffuse giants. Stars like Betelgeuse in the constellation Orion or Ui Scuti, located in the Scutum constellation, exemplify this stellar class. A red supergiant, if placed at the center of our solar system in the Sun's position, would easily swallow Mars, and in some cases, even Jupiter. Their characteristic cool, ruddy glow is a telltale sign of their relatively low surface temperature compared to other stars. This red hue also signals that a star is nearing its final act, a prelude to a spectacular supernova event. As these giants age, their cores become increasingly dense, eventually filling with iron. At this point, the star's internal nuclear fusion can no longer counteract the relentless force of gravity. Gravity wins this cosmic tug-of-war, triggering a catastrophic core collapse. This collapse results in a supernova, a colossal explosion that briefly outshines entire galaxies with its brilliance. The immense energy unleashed during these blasts forges the heaviest elements in the universe, elements heavier than iron. These newly created elements, along with the star's remaining material, are then scattered far and wide across the vast expanse of space. In essence, red supergiants are ticking time bombs, cosmic powder kegs on the verge of detonation. They are cosmic fireworks displays just waiting for their moment to erupt in a blaze of glory, enriching the universe with their stellar legacy. And that's our whirlwind tour of the galaxy's strangest stars. From magnetars to red supergiants, each reveals the wild creativity of the cosmos. We are all made of stardust from these stellar oddities, stay curious, keep exploring, and remember, the universe is always stranger than we imagine. Until next time, keep...
Imagine a dance floor so vast it stretches for billions of light years, where the dancers are galaxies, each a swirling collection of hundreds of billions of stars. These cosmic dancers move with a powerful, transformative grace, drawn together by gravity in a performance that's been ongoing since the dawn of time. Sometimes, galaxies spiral toward each other, beginning a slow approach that can last millions of years, a prelude to a spectacular galactic collision. This isn't just destruction, it's magnificent creation. When we look deep into the sky, we see galaxies with arms stretched by gravity, merging in chaotic, beautiful messes. The universe is dynamic, alive, and constantly evolving. Galactic collisions are a key driver of this change. These events involve structures hundreds of thousands of light years across, containing trillions of suns. Yet the process is surprisingly slow and delicate. Stars rarely collide. Instead, the drama unfolds in the vast clouds of gas and dust. So, what happens when these immense islands of stars are drawn together? It's a story of tidal forces, stellar fireworks, and the birth of new worlds. This cosmic ballet shapes the very fabric of the universe and even foretells the distant future of our own Milky Way. Prepare to witness the awesome power and breathtaking beauty of galaxies in collision. To appreciate galactic collisions, we first need to understand galaxies themselves. Think of a galaxy as a colossal city of stars, gas, dust, and dark matter, all bound by gravity. Our Sun is just one of hundreds of billions in the Milky Way, one of 2 trillion galaxies in the observable universe. Galaxies come in many shapes: majestic spirals like the Milky Way, giant ellipticals, and chaotic irregulars. Gravity is the architect, but dark matter is the invisible glue holding galaxies together. When you look up at the Milky Way, you're seeing your home from inside one of these star cities. And this city is moving, on a path that will one day lead to a spectacular cosmic encounter. Galaxies aren't isolated. They're grouped in clusters, moving and interacting under gravity's influence. Our Milky Way is part of the local group, pulled by the gravity of its neighbors. Sometimes galaxies collide. Larger ones devour smaller ones, while equals merge in slow-motion encounters. As 2 galaxies approach, tidal forces stretch and distort them, drawing out long streamers of stars and gas. These gravitational dances can last hundreds of millions of years, with galaxies swinging past each other before finally merging. Each pass strips away more stars and gas, until they become a single, larger entity. For many galaxies, including our own, collision is not a matter of if, but when. The universe's dance floor is always active, choreographed by gravity. When 2 galaxies collide, it's not a demolition derby. Stars almost never crash. The real action is in the vast clouds of gas and dust, which slam together and trigger massive shockwaves. This compression ignites bursts of star formation, lighting up the merging galaxies with millions of newborn suns, a starburst galaxy. The elegant spiral arms are torn apart, stars thrown into new orbits, and the original galaxies lose their identities. Over time, chaos gives way to order as gravity reshapes the jumble into a new, larger galaxy. Often, 2 spirals merge into a giant elliptical, their star-forming gas spent in the initial burst. Galactic collisions are engines of creation, seeding the cosmos with new generations of stars. The cosmic dance ends with a fundamentally different galaxy, bigger, rounder, and forever changed. This is how the universe renews itself. This isn't just a distant phenomenon. It's our future. The Milky Way is on a collision course with the Andromeda Galaxy, set to begin in about 4.5 billion years. When it happens, the night sky will be filled with the stars of another galaxy, and a spectacular burst of star formation will light up the heavens. Our solar system will likely survive, though it may be flung into a new orbit. By then, our sun will be nearing its end, and Earth may already be uninhabitable. The merged galaxy, nicknamed Milky Way, will be a testament to cosmic evolution. Studying these collisions reveals how galaxies grow, change, and create new stars, showing us the universe is always in motion. We are part of this grand story, living inside one of the dancers, connected to the universe's most powerful forces. Picture our solar system a star at the center, planets orbiting in a precise gravitational dance. The sun's gravity keeps everything in place from Mercury to Neptune. Each planet follows its own path, creating a stable, predictable system. Earth's orbit gives us seasons and the conditions for life. All planets are bound by gravity, moving together through space. Think of it as a cosmic carousel. The sun is the center, planets are the riders. This relationship defines what it means to be a planet world that belong to a star, warmed by its light. But the universe isn't always so orderly. Sometimes planets are torn from this dance. They're cast out, leaving their solar family behind. These exiled worlds drift alone, far from any star. Their journey is cold, dark, and endless. Most planets remain loyal companions to their stars. But a few are destined for a different fate. They become cosmic exiles, wandering the interstellar void. This is the story of the rogue planet. What is a rogue planet? It's a world that doesn't orbit a star. Instead, it drifts alone through the galaxy, untethered, cold, and dark. No sunrise, no warmth, just endless night. These planets are also called interstellar or free-floating planets. Their defining feature is solitude. Imagine Earth without the sun, frozen, shrouded in darkness. Rogue planets glide silently, guided only by the galaxy's gravity. Picture a child leaving a family game, wandering off alone. That's a rogue planet. They come in all sizes, from tiny icy bodies to massive gas giants. The Milky Way could be filled with billions, even trillions of these hidden wanderers. Some estimates suggest they might outnumber the stars themselves. They're a silent, unseen population, an undiscovered frontier. We're only beginning to explore their mysteries. Each rogue planet is a lonely traveler lost in the vastness of space. Their existence challenges our understanding of what it means to be a planet. How does a planet become a rogue? It usually starts in the chaotic early years of a solar system. Young planets jostle for position, their orbits unstable. Sometimes, a close encounter between giants like Jupiter can fling a smaller planet away. It's cosmic billiards. One planet is ejected, the other settles in. A planet can also go rogue if its star dies or if a passing star disrupts the system. The result, a world stripped of its home, set adrift in the galaxy. Our own solar system may have lost planets this way long ago. These violent events shape the architecture of planetary systems. The calm we see today hides a turbulent past. Rogue planets are reminders of the universe's dynamic nature. Their journeys begin with chaos and end in solitude. Each one is a survivor of cosmic upheaval. Finding rogue planets is a challenge. They're dark, cold, and nearly invisible. Astronomers rely on gravity to spot them. The key technique is gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity bends and magnifies the star's light. For a brief moment, the star appears to brighten. This is the planet's signature. Detecting these events requires monitoring millions of stars night after night. It's like searching for a needle in a cosmic haystack. Future telescopes, like the Nancy Grace Roman Space Telescope, will revolutionize this search. They'll find thousands of microlensing events revealing hundreds of rogue planets. For the first time, we'll begin to count these hidden worlds. We'll learn their sizes, their origins, and their place in the galaxy. The hunt is just beginning. Soon, the darkest corners of space will give up their secrets. Rogue planets are more than cosmic oddities. They're scientific gold mines. Each one is a time capsule from a lost solar system. Studying them reveals how planets form and how systems evolve. They hold clues to the violent processes that shape the cosmos. Could a rogue planet harbor life? It seems unlikely, but a large planet with a thick atmosphere might keep a hidden ocean warm beneath its icy surface. Life could exist in darkness, drawing energy from chemical vents, just like in Earth's deep oceans. This possibility expands our idea of where life might thrive. Rogue planets challenge our assumptions about habitability. Every discovery opens new questions about our place in the universe. These silent wanderers are survivors, carrying stories of chaos and resilience. As we find more of them, we'll learn about our own origins and the potential for life beyond the stars. The universe is full of lost worlds, each with a story waiting to be told. We are creatures of curiosity, gazing at the night sky and wondering about our beginnings and our end. Where did all this come from? Will the universe last forever, or could it all end suddenly or slowly? This isn't just idle speculation. It's a core question of modern cosmology. The universe, like everything we know, might have a lifespan. Science seeks answers not with prophecy but with evidence, by studying distant galaxies, the afterglow of the Big Bang, and the forces that shape reality. The universe is not static. It's expanding, evolving, and its current state holds clues to its fate. To understand if a sudden collapse is possible, we must first grasp the universe's present behavior. Its relentless expansion is the starting point for any discussion about its destiny. So, could everything we know vanish in an instant? Let's find out. Our understanding of the universe's fate began with a revolutionary discovery. Galaxies are moving away from us. This redshift, first observed by Edwin Hubble, revealed that space itself is stretching. The universe is like rising bread. Every galaxy moves away from every other, not through space, but with space. For decades, scientists wondered if gravity would eventually halt this expansion and reverse it. But in the late 1990s, astronomers found the expansion is actually accelerating. This shocking discovery pointed to a mysterious force, dark energy, pushing everything apart. Dark energy now dominates the cosmos, driving its expansion faster and faster. The future of the universe depends on the balance between gravity and this relentless, invisible force. The question shifted. Will dark energy keep winning, or could something change? The answer shapes every theory about the universe's end. Before dark energy, the leading theory for the universe's end was the Big Crunch, a reversal of the Big Bang. Gravity would eventually halt expansion, pulling everything back into a fiery collapse. But there's a more dramatic idea, a sudden collapse, triggered not by gravity, but by a change in the universe's fundamental state. This involves vacuum decay, a shift from our current false vacuum to a true lower energy state. If such a transition began, a bubble of new physics would expand at light speed, erasing everything in its path. There'd be no warning. One moment the universe exists, the next it's gone. This unsettling scenario comes from quantum field theory, not science fiction. It's instantaneous, undetectable, and would rewrite the laws of reality. But how likely is it? For a sudden collapse, the Higgs field is key. It gives particles mass and may be only metastable. Our universe could be like a pencil balanced on its tip, stable for now, but vulnerable to a nudge. What could trigger the fall? Perhaps a microscopic black hole or a colossal cosmic collision, both requiring unimaginable energy. The energy barrier protecting our vacuum is immense, far beyond anything seen in supernovae or black hole mergers. The stability depends on the precise masses of the Higgs boson and the top quark. Current measurements place us on the edge, long-lived but not absolutely stable. If the Higgs were heavier, we'd be safe, lighter, and collapse might have already happened. For now, the universe's precarious balance holds. Most physicists agree a sudden collapse is extremely unlikely. The universe's vacuum appears stable for trillions upon trillions of years, far outlasting stars, planets, and even galaxies. Despite countless cosmic cataclysms, nothing has triggered vacuum decay. Dark energy, meanwhile, is pushing the universe toward a cold, empty big freeze, not a fiery collapse. For a sudden end, dark energy would have to reverse, something we have no evidence for, so we can rest easy. The universe's end is a fascinating theory, not an imminent threat. The timescales are so vast, humanity will be long gone before it matters. Our concerns remain local, not cosmic, at least for now.
Imagine a star, far more massive than our sun, a celestial behemoth burning with incredible intensity. These stellar giants live fast and die young, consuming their fuel at an astonishing rate. But what happens when one of these massive stars exhausts its nuclear fuel? It collapses under its own gravity at the end of its life, triggering a spectacular supernova explosion. The result, if the star is massive enough, a black hole. A black hole is a region where gravity is so intense that nothing, not even light, can escape its relentless pull. It's a point of no return in the fabric of space-time. Black holes aren't empty voids. They're matter crushed into an incredibly small space. a singularity where the known laws of physics break down. This singularity is surrounded by the event horizon, the black hole's boundary. Cross that boundary, and there's no return. You're forever trapped within its gravitational embrace. These are the remnants of massive stars, the final stage in a cosmic drama of epic proportions. They warp space and time in ways that defy our everyday experience, creating gravitational fields of unimaginable strength. Einstein's theory of general relativity predicted their existence.